Hi, everyone. Welcome to the webinar. We're very pleased to have Kamil Ryduchowski from Warsaw, and he's speaking on equilateral and separated sets in non-separable Banach spaces. Kamil?
Thank you for the opportunity to give this talk. I will try to show my slides. Okay, I think I got it. So yeah, I'm going to talk about equilateral and separated sets in some non-separable Banach spaces. And the talk is based on a joint work with Piotr Koszmider. And well, first let me pick some notation. So first of all, the first uncountable cardinal is denoted by omega1. If we have a sequence of reals of length omega1, then its support is the set of those coordinates on which the sequence is non-zero. And by C00 omega1, we denote the set of those sequences of length omega1 which have finite supports. If X is a Banach space, then Bx denotes the closed unit ball and Sx denotes the unit sphere. Most of the notation is pretty standard. By a subspace, I will always mean a closed linear subspace, and by an operator, I will always mean a linear and bounded operator. If X is a set, then by X less omega, I denote the family of all finite subset of X, and X to the power n, I denote the family of all n element subset of X. And a last piece of notation, the last one, is that if A, B are disjoint sets, then by AO times B, I denote the sets of unordered pairs, such that the first element is from A and the second is from B. So like the Cartesian product, but with unordered pairs. Okay, so the main object of interest for me are the following subsets of Banach spaces. Let X be a Banach space, and let's choose some positive number delta. A subset A of X is delta equilateral if any two points are in the distance exactly delta from each other. It is delta separated if any two of its points are in the distance at least delta from each other. And it is delta plus separated if any two distinct points are in the distance greater than delta from each other. I will say that set is equilateral if there is a delta such that it is delta equilateral. Let us also note that if you have any equilateral set in Banach space, then we may always we have a Banach space and some infinite equilateral set. Then we may always assume that this set is a subset of its unit sphere. Namely, we can scale it so it becomes one equilateral and then move one of its points to 0 and forget about it, and all the other points are on the unit sphere. So what's known about those kinds of sets? So first, let us look at the separable case. So Terenzi constructed an equivalent renorming of L1 without infinite equilateral sets. So it's not the case that any infinite dimensional Banach space contains an infinite equilateral set. But there are some positive results, namely Merkourakis and Vassiliadis prove that a Banach space containing an isomorphic copy of C0 always admits an infinite equilateral set. And Freeman, Odell, Sarli, and Schlumprecht prove that infinite dimensional uniformly smooth Banach spaces also do admit infinite equilateral sets. So now let's have a look at separated sets. Well, obviously the classical Lis lemma tells us that the unit sphere of every infinite dimensional Banach space contains an infinite 1 minus epsilon separated set for any epsilon greater than 0. There is a result of Kotman that the unit sphere of every infinite dimensional Banach space contains an infinite 1 plus separated set. And probably the most remarkable from the most remarkable result of this kind is the result by Elton and Odell that the unit sphere of every infinite dimensional Banach space contains an infinite 1 plus epsilon separated set for that's a type. Obviously it should be for some epsilon greater than 0. This epsilon depends on the Banach space. On this X, although there is a result by Klitschka and Plus that for non-reflexive infinite dimensional Banach spaces, non-reflexive is also infinite dimensional, then those epsilon can be chose to uniformly for non-reflexive spaces. It may be any number smaller than, well, this number. Okay. So what's happening in the non-separable case? So there's a result of Schmidt and work talked about it on this webinar, that there is an equivalent renorming of L1 of density continuum without infinite equilateral sets. And for example, whether every C of K for K compact Hausdorff admits an uncountable equilateral set, it is independent of ZFC. It is a result of Schmidt. So, well, what I find kind of provoking is that every example and every consistent example of a non-separable Banach space without uncountable equilateral sets so far was not even WLD, let alone reflexive. And I find it kind of provoking because, well, let's see what happens with separated sets in this non-separable setup. So first of all, Elton and Odell noticed that C0 omega 1 doesn't contain an uncountable 1 plus epsilon separated set for any epsilon. So, well, it shows that their theorem that any infinite dimensional Banach space contains an infinite 1 plus epsilon separated set can't be like generalized that for any density kappa, the Banach space of density kappa contains uncountable 1 plus epsilon separated set of size kappa. And yeah, I didn't write it, unfortunately. From this point on, we consider those sets only in the unit sphere. So the result is that the unit sphere of the space C0 omega 1 doesn't contain such a set. Also, there's a result of Guzman, Kruszek, and Koschmidt, a very recent one actually, that there is a Banach space of density continuum such that its unit sphere can be divided into countably many sets of diameter less than 1. So in particular, in the unit sphere, if you have any uncountable subset of the unit sphere, then, well, uncountably many of its elements have to come from one of those countably many sets. So they have be closer than 1 from each other. So there's not even uncountable 1 separated sets in the unit sphere of this space. But there is a very strong positive results by Hayek, Kania, and Russo that the unit sphere of every non-separable reflexive Banach space contains an uncountable 1 plus epsilon separated set for some epsilon depending on x. This result of Hayek, Kania, and Russo shows that strong isomorphic properties, such as reflexivity, force some geometric properties or isometric properties, such as having large separated sets, 1 plus epsilon separated sets. So this lack of reflexive or even WLD examples of non-separable Banach spaces without uncountable equilateral sets made us consider whether perhaps reflexivity forces the existence of uncountable equilateral sets, but that's not the case. And our results are that, well, first of all, let me recall that a Banach space is Hilbert generated if there is a Hilbert space, and H and an operator T from H into X with dense range. So, okay, our result is consistent only. We were not able to have that in ZFC alone. So let's assume that there is a non-meager set of reals of size Aleph1. For example, assume the continuum hypothesis. Then there is an equivalent renorming of the Hilbert space L2 of omega 1 without uncountable equilateral sets. So, well, obviously the Hilbert space is super reflexive, etc. So any nice isomorphic property. And now, well, let's say that we want neither equilateral nor separated sets. How good examples can we have? By this result of Hayek, Kania, and Russo, we can't have reflexive, but we've been able to get a Hilbert generated space such that it contains an isomorphic copy of L2 in every non-separable subspace, such that its unit sphere doesn't admit uncountable equilateral sets nor uncountable 1 plus epsilon separated sets. So that's as close to reflexivity as we were able to get. Let me mention that this property of having a copy of L2 in each non-separable subspace, it's kind of related to the notion of being somewhat reflexive, namely a Banach space is said to be almost reflexive, somewhat reflexive, if it contains a copy of L2 in every infinite dimensional subspace. In our example, it's not the case, but we have copies of L2 in non-separable subspaces. So now let me talk a bit about infinitary combinatorics, which is somehow a very useful tool in those problems. So first of all, let me recall that a delta system is a family of sets such that there is a fixed set delta known as the root of this delta system, such that any two sets from this family have intersection exactly delta. So a delta system is such a family that there is some root delta, some fragment that is a subset for every set in this family, and aside from delta, they're pairwise disjoint. And a very important lemma is the delta system lemma, proved by Shanin, that if you have any uncountable family of finite sets, then there is an uncountable delta system which is a subset of this family. So basically, we use that if you have some uncountable family of finite sets, we say that by passing to uncountable subfamily, we may assume that our family is a delta system, and then we have some nice combinatorial properties, so we can work with it. And let me show the proof of this observation by Elton and Odell, that the unit sphere of C0 omega 1 doesn't contain an uncountable 1 plus epsilon separated set for any epsilon. It is, I think, a good. It's a relatively simple example, but it shows how those tools from infinitary combinatorics can be used. So the proof is basically by making assumptions. Suppose we have an uncountable 1 plus epsilon separated set in the unit ball, actually. So if we have such a set, we may always assume that it is a subset of our favorite dense set. That's because if we have any 1 plus epsilon separated A, then by approximating elements of A, let's say epsilon over 4, close with elements from this dense set, we may construct an uncountable 1 plus epsilon over 2 separated set in this dense set. So in particular here, let's assume that A consists of vectors with finite supports and with rational values. Now, if we have this, then we may use the delta system lemma, and by passing to an uncountable subfamily, we may assume that the supports form a delta system. Now, since we have x's from A have rational values, then we may assume that on this finite subdelta, they all agree. But now we are done, because that basically means that when we look at x minus y, then, well, on delta, it is 0. And outside of delta, the supports were pairwise disjoint because it was a delta system. So that means that x minus y is 0 on delta, and there are some pieces that it looks like x, and there is a piece that it looks like y. So in particular, its infinity norm is at most maximum over those two, and they were from the unit ball, so it's at most 1, and we are done. Our set can be 1 plus epsilon separated. Okay, so now our spaces are constructed with the help of some colorings. So let me recall that omega 1 power 2 is just the family of all 2-element subsets of omega 1, so just all pairs from omega 1. And one may think of it as the edges in the complete graph with omega 1 vertices. And we have a coloring, so every edge gets a color, either 0 or 1. And we consider the family, denoted by AC, of all finite subsets of omega 1, which are 0 monochromatic, meaning that every edge between elements of A got color 0. So it's the family of those finite subsets of omega 1, such that they click in this full complete graph is 0 monochromatic. And we use it to construct a norm Well, the construction is based on constructions of Schellach and Steprans and Work, who considered this or very similar constructions in the context of Banach spaces admitting few operators, namely for x in C00 omega 1 by x norm with those index C. Well, we basically write the definition of the L2 norm, but instead of taking the supremum over all finite subsets of omega 1, we just take the supremum over all zero monochromatic subsets of omega 1. Since obviously we are taking supremum over less than all finite subsets, so this norm is less or equal than the L2 norm. On the other hand, all singletons are monochromatic in both colors, so it is at least the infinity norm. Also, if x is a vector which has a zero monochromatic support, then here we have equality, because obviously to calculate the norm of x, it is important only to look what happens with subsets of the support. And similarly, if the support of x is one monochromatic, so no edge have color 0, then the first inequality is in fact an equality. And by xc, we denote the completion of C00 omega 1 with respect to this norm. Okay, so that's the very general construction, but to our for our purposes, we need some very strong properties of the coloring, so that the induced norm will be very chaotic. And the property is as follows. Oh, okay, sorry. First, let us just know that due to this inequality, xc is a Hilbert-generated Banach space. Just take the identity from L2 omega 1 into xc, and the second norm plus the C norm is an equivalent norm on the Hilbert space L2 omega 1. So that's a bit of a spoiler how our renorming of L2 omega 1 will be defined. Okay, so back to this chaotic properties of the coloring. Let me recall that AO times B is the family of all pairs with one element from A, the other from B, or you can think of it as all the edges connecting A and B in this uncountable complete graph. So a coloring C of this complete graph with omega 1 vertices into two colors is a strong T coloring if given any uncountable pairwise disjoint family of finite subsets of omega 1. There are two distinct sets in this family such that all the edges between them have color 0, and there are two distinct elements of this family such that all the edges between them gets color 1. So that's a very strong property of the coloring, and in fact it is so strong that it is independent of ZFC whether such a coloring exists. So it's been known for some time now, it's a result of Galvin, that under the continuum hypothesis there is such a coloring. It follows from a very recent result by Kochman, Rinot, and Steprans that the existence of a non-meager set of reals of size omega 1 is enough to make sure that there is a strong T coloring. And on the other hand, and I think it's folklore, that under Martin's axiom and the negation of the continuum hypothesis, there is no strong T-coloring. So it is really consistent and only consistent. Okay, so the first step is obviously to take this definition of a strong T-coloring and somehow translate it to some properties of this induced norm XC, or the C norm. This is actually very natural. We have the following lemma. So first, the assumptions. Suppose we have a C is a strong T-coloring, and we have an uncountable sequence of vectors from the space XC with finite pairwise disjoint supports. And for the convenience, let's assume that they are all of the same norm R. That's not really important. Then there are two vectors in this family which are in the distance precisely square root of 2R. And there are two vectors such that they are in the distance R from each other. And the proof is very natural. We have this uncountable sequence of vectors, and they have finite pairwise disjoint supports. So by the definition of a strong T-coloring, there are two supports such that all the edges between them gets color 0, which gives us this L2 style behavior, namely this equality. And there are two supports such that all the edges between them get color 1, and this gives us this the infinity norm style behavior, so the equality with R here. Okay, so how, let's see a bit of a sketch of the proof that if we equip the Hilbert space L2 of omega 1 with the norm, which is just the sum of the L2 norm and the C norm, where C is a strong T-coloring, then such a space doesn't contain uncountable equilateral sets. So, well, as I mentioned at the very beginning, it is enough to prove that its unit sphere doesn't contain such a set. So, well, take any non-separable subset of the sphere, and we will find 4 vectors which show that this set is not equilateral. And the proof is very similar to the proof of this observation due to Elton and Odell about C0 of omega 1. So first of all, let's inductively pick X alphas in A, and for a bit of technical reason, an intrinsic sequence gamma alpha of ordinal numbers such that X alpha of gamma alpha is non-zero. Then approximate it. Oh, okay. First, by passing an uncountable subfamily, we may always assume that we are separated from zero, since those are non-zero numbers. Now approximate it well enough with vectors with finite supports and rational values, so as in the proof. And here well enough means not only in the norm, but also to make sure that this value on those picked coordinates is still above epsilon. Now, once again, we use the delta system lemma so that we may assume that those supports of those y alphas form a delta system. And once again, by passing to an uncountable subfamily, we may assume that they all agree on the root of the delta system. And now just project y alphas outside of the root. So just those z alphas are 0 on the root, on delta, and equal to y alphas everywhere else. And then basically what we managed to got here is that Z alphas now have finite supports because Y alphas already had, but they also have pairwise disjoint supports because Y alphas, the supports of Y alphas formed a delta system, which means that there was this common delta in each of them, and apart from that, they were pairwise disjoint. So now we get rid of the root, and now we have pairwise disjoint supports. We may once again assume that the C norms of Z alphas are all equal, and in fact that the two norms also are equal, but we are in position to apply the lemma. So we will get that some Z alphas are R from each other with respect to the C norm, and some are in the distance squared of 2R from each other with respect to the C norm. All this fun with gamma alphas were to make sure that the moment we pass from Y alphas to Z alphas, so we remove the root, potentially a very large part of the L2 norm might have been focused, centered on the root, so it may change, and the C norm may be very well dominated by the standard L2 norm. So all those gammas alphas are just to kind of make sure that this impact of the C norm is significant enough that those shenanigans we're doing with it are visible to the whole norm, which is the sum. Okay, there's also those property that every non-separable subspace of XC contains an isomorphic copy of L2. And this proof is a nice combination of results from Banach space theory and infinitary combinatorics. So first of all, use the fact that Y is WLD to find an uncountable sets of vectors with pairwise disjoint supports. Obviously, one may assume that they are of norm 1 just by normalizing them. And well, how do you do this? Since Y is WLD, there is this necessarily uncountable linearly dense sets such that every functional of is countably supported on this set. So one may look at coordinate functionals and just inductively pick such Y alphas from this set. So if you have already in hand those Y alphas of norm 1 with pairwise disjoint supports, now let's pick A alphas supports included in the support of Y alphas to be finite zero monochromatic, such that, well, the norm, the C norm is the supremum over such things. So just take something that, since the supremum is 1, just pick a witness that it is at least 1/2. And then one may consider another coloring, in fact, namely coloring F, which on the pair psi eta is 0 if and only if C was 0 on all the edges connecting A psi and A eta. Since C is a strong T-coloring, it meant that if we take uncountably many A etas, then there are always 2 such that all the edges between them have color 0. So this situation here happens in every uncountable sets of A etas, or in other words, the coloring F doesn't admit uncountable one monochromatic sets. And there is a result by Erdős, Dusznik, and Miller that if we have such a coloring that doesn't admit uncountable one equilateral sets, then it has to admit an infinite zero monochromatic set. And while being zero monochromatic for F, it just means we had those zero monochromatic A alphas, and now all the edges between them have color zero. So that just means that the union of those xi's in I is zero monochromatic for C, and then it can be checked that those xi's span a copy of L2. That's more or less the fact that our norm behaved like L2 norm on zero monochromatic sets and like the infinity norm on one monochromatic sets. Obviously, there are some details to check, but I think they're not that important. Okay, now I think I'm done proving things, but actually I think the statement, it's nice. It is kind of well, I think I've first seen a similar statement in this paper by Guzman, Hruszak, and Koszmider. Namely, it is a proposition that deals at once with admitting both 1 plus epsilon separated sets and equilateral sets. And the statement is as follows: that in our space XC, for every positive delta, there is a positive epsilon, such that for every uncountable 1 minus epsilon separated subset of the unit sphere, there are x1, x2, x3, x4 in A, such that and the distance between x1 and x2 is, well, intuitively speaking, close to square root of 2, and the distance between x3 and x4 is, intuitively speaking, very close to 1. So first of all, clearly it follows that there is no uncountable one equilateral sets in the unit sphere, and as I mentioned at the beginning, it means that there are no uncountable equilateral sets at all. And on the other hand, there can't be uncountable 1 plus delta separated sets just because of this condition. So from this proposition, it follows that in our space XC, in the unit sphere doesn't admit nor equilateral nor separated uncountable sets. Okay, but this idea with colorings has certain limitations. Namely, the obvious thing is that those results are only consistent because all of them need a strong decoloring. And under this construction, it is necessary, namely, we prove that under some set theoretic axioms, namely Martin's axiom and the negation of the continuum hypothesis, for every such a coloring of this type, the space XC, well, if it doesn't contain an isometrically isomorphic copy of C0 omega 1, then its unit sphere contains an uncountable square root of 2 equilateral set. So this is such a set that it is both equilateral and 1 plus something separated. So basically, nothing interesting in terms of those separated or equilateral set happens in those spaces under Martin's axiom and the negation of the continuum hypothesis. So with our approach, best we could do is consistent. And finally, I wanted to ask you some questions, actually. So first of all, what happens in the separable case? So is there an infinite dimensional reflexive Banach space without an infinite equilateral set? There are examples, the one I mentioned of Terenzi, of infinite dimensional but very non-reflexive Banach spaces without an infinite equilateral sets. There are also other examples by Merkoutakis and Vassiliadis, I think, but there are no reflexive examples as far as I know. And the other question is, well, is there a non-separable reflexive or Hilbert generated or weakly compactly generated on weakly Lindelof determined Banach space without uncountable equilateral sets? So obviously our results yield that consistently yes, but what happens in ZFC alone? The next question is about, well, is there an inseparable reflexive or again Hilbert generated, weakly compactly generated, etc. Banach space whose unit sphere does not admit an uncountable 1+ separated set, because, well, those spaces we considered, in all the cases we managed to prove something, that they always have 1+ separated sets in the unit sphere. And all the examples that do not have, there are some absolute meaning in ZFC examples, for example, in this paper by Guzman, Hruszak, and Koschmider, but they are not reflexive. So the question is about basically nice isomorphic properties. The last question is, can you do in ZFC what we consistently did? So the renorming of precisely L2 omega 1 without uncountable equilateral sets. And the last question, well, is there an equivalent renorming of C0 omega 1 without uncountable equilateral sets? So for a standard separable C0, it is a result by Merkoutakis and Vassiliadis that under every equivalent renorming, C0 admits infinite equilateral sets. But the proof is, I would say, of very separable nature. I wasn't able to find any argument that instantly gives that it is also true for this space. I don't know whether it is true, so I don't know. Perhaps some of you will know. Okay, and I also have some selected references. So there is our preprint. There you can read, for example, on those spaces with few operators. I discussed that our definition follows definitions of Schellach, Steprans, and Work. In particular, the spaces XC we consider admit few operators in some sense. And well, I talked about quite a few results here, so I wasn't able to put all the references such that it will be readable. So there are a few which are quite recent, and I find they quite and I find them very interesting. So those are the results that I think they are the strongest one which I talked here today. Obviously, much more references are in the paper, and I think it's all I have. So thank you for your attention.
Oh, thank you so much. That was a beautiful talk. Are there any questions or comments? Okay, I guess not. Well, I want to thank you again, Kamil. That was a really nice talk. And so let me stop recording now then.